Today's lesson is on measuring lines that are related to circles. And the lesson has 4 parts. First, we're going to talk about lines and circles and how they can interact. One of the types of things we're going to find out is about chords, and we're going to talk about how to measure intersecting chords. We'll also find out about something called secants, and we're going to learn how to measure intersecting secants. And then finally, we're going to learn about something called a tangent, and we're going to learn how to measure intersecting when a secant and a tangent intersect. And finally, we'll see that that last one is actually the same as intersecting secants. It's just a special case. So when I look at lines and circles, we can see that there are 3 types of line segments that can interact with a circle. The first is called a tangent, and that's when it touches the circle at one point. And that's an example of a tangent. That line is a tangent to the circle. The second type of line segment is a secant. A secant cuts the circle at 2 points. And there's an example. Notice that the line goes all the way through the circle, and it goes in both directions away from the circle. Part of a secant, the part inside, is called a chord. So a chord has endpoints on the circle, so it looks like that. Every secant has a chord in it. Now we're going to talk about how to measure intersecting chords. And what we determine is that the product of the lengths of the parts of a chord is equal to the product of the lengths of the parts of the chord that intersected with it. Wow, what does that mean? Well, here's an example of a circle where I've drawn 2 chords. And I'm going to label those parts A and B on one chord, and C and D on the other chord. And all this means is that if I take the product of the first chord, AB, it's going to be the product of the second chord, DC. So AB equals CD. Now let's do an actual example of a problem using this. So imagine if we had A equals 4, B equals 6, C equals 8, and we're asked to find what D is. So we'll call D as X. So my first step is using my equation of AB equals CD. I plug it in. So 4 times 6 equals 8 times x, or 8x. Multiply that out, I get 24 equals 8x. Divide both sides by 8, and finally I get my answer of 3. So that length of that chord segment there is 3. Next, we're going to learn how to measure intersecting secants. And when 2 secants have a common endpoint, the product of one external part of the secant times the whole secant is equal to the external part of the other secant times the whole other secant. Wow, I thought the one for chords was wordy. This one's really ridiculous. But again, when I actually draw a picture and look at it, it's not that complex. So here's an example of a circle with 2 secants with a common endpoint. And we're going to label the parts again, A, B, C, and D. What this is saying is that if I take the part outside of one, A, and multiply it by the whole secant, A plus B, that's equal to the part outside for the other secant, C, times the whole secant, C plus D. Now, let's use that in an example problem. So, in this case, we'll say that A equals 7, B equals 11, C equals 6, and we're being asked to find D, so we'll call it X. So the first thing I'm going to do is write down my formula from the previous slide. And now I just have to plug in the various values. So A equals 7, B equals 11, C equals 6. And so I get this. I'm going to add up the 7 plus 11 on the left side to get 18, and I'm going to distribute the 6 on the right side. So on the left side I'm going to have 7 times 18, And on the right side, 6 times 6 is 36, and 6 times x is 6x. I have to make sure to distribute the 6 across both terms. Just multiply 7 times 18, I get 126. Subtract 36 from both sides, and I get 90 equals 6x. Divide both sides by 6, and I come up with my final answer of 15. So in this example, D equals 15. So now we're going to talk about a special case of the thing we just learned when one of the secants is actually not a secant, but a tangent. So here is what we've seen before. This is what we learned on the previous slide, A, B, C, D. But now let me replace that with an example where now AB is not a secant, rather it is a tangent. So what is B? Well, the value of B, since it just touches, it's a point, the length of B, the length of a point, it has no dimensions, is 0. So if B equals 0, in my formula, A plus B is the same thing as A plus 0, so the B just cancels out. And I'm left with simply A times A equals C times C plus D. A times A, of course, is A squared. So for this special case, we see that if I just take my tangent squared, it equals the outside portion of the secant times the entire secant. Now let's do an example problem of this one. So once again, I'm going to write down my formula, and in this example, I'm going to have A equals 15, B is going to be 0, of course, and C is going to be 9, and I'm being asked to find D, so I'll call that x. So I'm just going to plug in my values, first cross out my 0 for B, plug in my values, and I get 15 times 15 equals 9 times 9 plus x. On the left-hand side, I'm going to multiply 15, and 15 squared is 225. And on the right-hand side, I'm going to distribute my 9. So 9 times 9 is 81, and 9 times x is 9x. So I'm simply going to subtract 81 from both sides. And on the left side, I get 144. And on the right side, I'm left with 9x. If I divide by 9 on both sides, I end up with my final answer of 16 equals x, or x equals 16. So my answer is 16.